Swayam Prabha. Digital India. Educated India.
So similarly is the case of, okay, so now if I do this, then I get something like this. So I get 42 here, I get 42 replaced here, I get 42 replaced here, I get 42 replaced here. At all these places, I get 42 replaced. And now because I've replaced 42 everywhere, there is no instance of X anywhere. So if there is no X, then why do I need this statement? Forget this statement. So I remove that statement. Very good. So now what can I do? So now I see that Z1 is 42. So I can remember that Z1 is 42. And everywhere there is Z1, I can go and replace 42. I can see a Z1 here. See, I'm not even following control flow. I'm not going through the graph at all. I'm just looking at wherever I find a statement with a list-based analysis. Wherever I find a statement, I'm just going and replacing by 42. This is 42. Is Z1 anywhere there? I can't find it anywhere else. So I think this is all I can. Yeah, and I can also see that Z2 is 42. Interesting. Z2 is 42 as well. So wherever I can find Z2, I can go and replace 42. This is also 42. Right? So I go ahead and replace all this. And because I have replaced Z1 and I've replaced all occurrences of Z2, I can remove these statements. So the statements vanish. Very good. So now can I do something more? I see that no matter which choice you take, the magician always returns me 42. Right? It can return me 42 for the first argument, or it can return me 42 for the second argument. Right? So effectively the value of Z3 can only be 42. It cannot be anything else. So if this is 42, in that case, I can simply replace it by Z3 equal to 42. And if Z3 is 42, then I can go in the program and wherever I see Z3, I can go and replace it by 42. So Z3 is 42. Right? So I cannot do it for X yet because this X2 is preventing me, because magician can also return me X2. Right? So I cannot do it yet. So I do that. So again, this particular statement vanishes because I don't need it anymore. It can only return 42. So I go and return this by X2 is equal to, this X3 becomes 42. Very good. So now what do I do? So now this X2 is simply this expression 42 plus Y1. Like I said, it does not really matter. I don't even care about the control flow. Right? I can simply go and put anything anywhere now. Right? It's a list. It does not have any structure anymore. So I can go and replace wherever I find X2, I can go and replace it by the right hand side. So I can just say that X2 is nothing but 42 plus Y1. Why not? Right? So I just replace it. Why not? I can do that. Once I've done that, so now what can I do? So these two basic blocks are gone. Why do I need to keep these basic blocks if I'm not even executing any instruction there? One thing is that there is surely a conditional jump here, right? So there is an if some condition, then do this, go to L1, else go to L2. Something like that. Let's say this is L1, this is L2. But no matter if I go to L1, then also I'm coming here. If I go to L2, then also I'm coming here. No matter what I do, I come in here. So it does not really matter. I don't really need to keep these two branches. But there is one small thing, that the choice as to, remember the magician, what it does. The magician decides that if you're coming from the left branch, then it keeps the left argument. If you're coming from the right branch, it keeps the right argument. Similarly for this case. Right? We methodically did it everywhere. So now what the magician can do is, the transformer can do is that it can simply remove these basic blocks. It can simply say, I don't need these basic blocks, forget about them. If you remove these basic blocks, you can simply merge these blocks. Now, because these are two basic blocks, one after the other. And now this is actually one basic block, right? Because there is no other way to go. So if you execute this, then you surely execute this as well. So this, you can merge them into a single basic block. So that is what we have done. We have merged it into a single basic block. If you have merged it into a single basic block, now there is a small thing that which of these two are taken depends on this condition C that existed earlier. Earlier there was a go-to, but then it is a matter of a selection between these two candidates. So in some sense, I can actually write it as a conditional statement, as a ternary operator. So I can say if the condition holds, then you take the left argument. else you take the right argument for x3. Then I can say that, then I can go and wherever in the program x3 occurs, I can go and replace it by x3. So that is what we have done. And we replace, and wherever there is a y1, I can go and replace it by input. So the whole program becomes this. Program becomes that print if the condition is true, then input plus 42, else print 42, and the second argument print 42. So you see how the analysis moves so nicely when you have SSA. I did not even bother about how the control was flowing. I did not use anything from the control program. I just went about replacing the names by their corresponding expressions. And you showed us, you got this analysis. You do not know how analysis on a graph looks like. And I know Khedkar sir will actually take quite an amount of time to really set up the framework. It's a beautiful framework, but he'll take quite a bit of time setting up the framework and explaining things, doing the correctness proofs, and showing that this analysis actually does what it's supposed to do. It is quite non-trivial. It is quite sophisticated and very complicated. But this analysis you saw was much simpler than, I mean, you will see that it will be much simpler than what Khedkar sir will present on Monday. Did you sort of get an idea of how did it go? Any questions regarding this?
Is it the reason why we assume infinite number of registers in NLVM IR or any other IRs as well?
No, that has nothing to do with that. You have infinite number of registers because you have infinite number of variables. So you can have as many variables in the program, and then I don't have to really assign register. I mean, you can think of every variable as being one register. In fact, you get more variables because of temporaries that get inside. So it only says that I don't care about the actual machine architecture at the moment. Remember, I started saying that this is a machine independent optimization or machine independent phase. So I do not care about how many registers my machine has. That is all.
Okay.
Right? But in some senses, just to get back to your question, you can think of every renamed name as a virtual register. In fact, LLVM does that. LLVM uses the that terminology. So each of these renamed names basically is referred to as a register, as a virtual register.
Yes, that's why I was asking.
Yes, that is what it says. So it's a notation. It's just a definition. But every renamed variable is a register. It's not that why you need it. You need it because you don't want to do a register allocation at this moment. You can do a register allocation much later after you have done the more sophisticated analysis. You just want to delay that allocation for later. That's the reason you just have virtual registers. Now, there are two questions I have not answered. I have shown you all the magic, but I did not tell you that how do we construct this form? How do I, I remember, I said that there is this SSA construction phase and there is this out of SSA phases. I have not told you how to construct an SSA and how to destruct an SSA. That I should have told you, but I'm sorry, I do not have time to do that. And that's okay. I mean, you don't have to understand everything in compilers. So like this is the SSA construction part. So SSA construction has basically two questions: that where do you insert? First question is where do you insert fee nodes? Any answer? Any idea as to where do you think you should insert fee nodes? At least a trivial answer to this.
Probably where the branching merges.
Very good. So that is one possible case it looks like. That you have to because wherever the branching merges, you do not know what is happening here. So you need to insert a fee node. But see the case for Y. Even though the branching merged, for Y I did not need a fee node. I removed this fee node because I was getting the same value at both places from both sides. So that is surely a sufficient condition, but not a necessary condition. Right? So it's okay that you can go about in putting a fee everywhere, but that will bloat your representation. So there is a much better algorithm which says that what is the right place to insert a fee node. Again, it's quite technical. So you have to compute what are called iterated dominance frontiers. You have to compute what are called dominance frontiers. And so that is also calculated on the top of the dominance tree. And then you have to get whatever iterated from here, because you need to, you have to look at the chain of definitions and then insert fee nodes there. So the short answer is that I'll not give you an answer. But all I can say is, yes, the sufficient condition is to insert a fee node for all variables at all merge points, but that is an overkill. So you can actually get away from inserting fee functions at much fewer places. The second question is that what should be my arguments attached to each of the fee nodes? So the arguments attached to each of the fee nodes are nothing but what is the name for that corresponding variable which is flowing along each of these edges. So whatever flows along the left edge becomes the left parameter, what flows along the right edge becomes the right parameter. But again, how do you track the flow of information, the flow of names? That is somewhat, at least efficient algorithm for that is quite technical. Again, I'll not get into it. So you use some sort of a stack to keep track of these renamed variables, and then you try to assign them the right names. But again, I'll not get into this. So I have motivated what is an SSA form and why it is useful for optimizations, but I will not discuss the SSA construction algorithm. The SSA destruction algorithm is still more tricky. It is quite a bit of tricky, like very tricky, because one reason it is tricky is because people generally assume that when you have multiple fee nodes, it is as if it's a parallel assignment. You can do them in any order, but it is not strictly correct. And because of that, even the first algorithm which proposed SSA and SSA destruction, it had a small bug, and that bug had lasted for quite some time, and then people noticed it, and there have been multiple SSA destruction algorithms even as late as 2009. So the first algorithm was somewhere in the late 90s, or not late 90s, early 90s. So somewhere in 89 to 91 was, so 91 is the paper for the SSA construction, the seminal paper which talks about this nice thing. So, and as late as 2009, at least I know of a paper, and there are still papers coming out of more efficient algorithms of like fixing these bugs and getting an efficient destruction algorithm. And in fact, there is this conference called CGO, Code Generation and Optimization, which is one of the topmost compiler conferences, and it was, I think, the best paper award in somewhere in 2009 was the paper which actually does this destruction. So it's a pretty technical and pretty dicey business as to how to do this destruction and construction. Construction is relatively simple, but destruction is slightly more tricky. And but it gives you a lot of advantages. The optimizers in between, SSA-driven optimizers, are way more efficient than data flow-driven optimizers. So that is the reason we try to do this optimization. I will just leave with a small sales pitch that even our group, we have been working on some variants of SSA forms, and one of the variants that we published in, so these are slightly old work that we published in CC 2009, and one of my students extended that work and published in 2016. And we essentially have an extended version of SSA, which we call the hot path SSA, which can do more. It can actually not only track the definitions like this, it gives you an SSA-like form, even when you want to track things more than just single control flows. Like, for example, in this case, one interesting case is that a lot of times your programs were interested in frequent paths, like which paths are executed very frequently. Like, for example, one thing could be that, let's say you are running a program, every run of the program is generating some data, and then you're collecting a lot of data out of each run, right? And then let us say you're using a machine learning algorithm to train on that data and do something useful on it. Now, it does not matter that if few of the data points are wrong, right? Even if the program ran incorrectly and some of the data points came out to be wrong, it does not matter so much, because your learning algorithm eventually is robust to noise. It will still learn a good model eventually. So, in fact, so this is a very simple case I'm putting across, but then there can be more interesting cases where people do this. You can actually predict that the program will do something like this, create a very efficient version of the program which will run across the fast versions, across the fast execution or the most common cases. And if at all, sometime you get to a slow execution, then the system will detect it and then try to retry a slower version, right? So there are algorithms which can do such things. So that is why it is important so there are optimizers which can do such optimizations, and to drive them, we need an SSA-like form. So we did not have an SSA-like form for the cases, and it becomes very, very tricky to do that, because it is not just earlier, if you do a data flow graph-driven analysis, you need the control flow graph and you need the 3 address code instructions. But if you're doing such an analysis, you also have to need the frequent path information, which are the most frequent paths. So what we did is that we collapsed these three into a single representation, which is again a list-like SSA representation, which we call the HPSSA form. And the trick to do that was to essentially come up with, like you have phi nodes, to come up with something called tau nodes. And what these tau nodes do is they essentially keep track of information that is coming across frequent paths. Like for example, in this case, it is saying that I know that the total information coming to it is x3, which could be either x1 or x2. But then I know, so this red line is the frequent path. But I know that most of the time the information coming is x1. Like this branch will execute very, very frequently, and it is very unlikely that you will ever get x2 coming in. And it inserts this tau nodes, which allows the optimizer to do optimizations, which can actually give you really aggressive optimized codes, which are tuned for these frequent paths. Right. So, like, if you're interested, I mean, you can go and look at these papers. I'll be very happy to discuss in case you are, if you want to talk. So with this, I am sort of over time, 7 minutes over time, not too bad. I thought I'd be much more. But with that, I'll end this session on control flow analysis and SSA construction. I just hope I have, I've tried to follow Professor Ramkrishna's instructions as much as possible to ensure that this sort of falls in the right place and like glues the two ends of the workshop together on both the parts or both the ends. I hope I have done my job. I'll be happy to fill in any gaps if I've left. But have a great time in the rest of the summer school, and I'll be very happy to take any more questions that you might have.
Thank you very much, Professor Subhajit. Very nice, very enlightening talk. Let's wait for some questions.
I had a question, like just to understand all the optimization that we did in the constant propagation thing, like converting it into ternary and then like replacing everything. There's algorithm for all of these, right? Like
no, so here I did not even follow any algorithm. I mean, what the algorithm I followed was simple replacement. I just said go and replace it. The algorithm was that you have x1, right? You go and replace x1 by its RHS wherever you can. That's it, nothing else.
yeah, that's fine, but like conversion from an if loop to the ternary thing.
That can be a pattern match. That can simply be a pattern match. That's just a pattern, right?
Okay.
So there are such optimizations which are called like, well, it's done low level code. It's done in sort of what are called people optimizations, and even at the higher level you can do it. I mean, in fact, there are other. You will actually do some of these optimizations in the next week anyway. But most of the time, I have not relied on any sophisticated analysis or any sophisticated algorithm for this optimization. These are mostly pattern matching and replacing. That's all I used.
Yes, understood. And for the phi thing, like the compiler basically understands the meaning of phi, like in the backend it has to interpret.
Yes.
Okay. Thank you so much.
So I have one question regarding your work. So, like, from where did you get this frequent analysis information? Like, how do you know?
Where did I get what analysis?
Like the frequency data also you're using, right?
Oh, acha, where did you get the frequency information? Okay, so there is something called, so you can do something called profiling. So what is profiling is basically you run the program on some sort of representative inputs and run it on a large suite, like on a large set of examples. And then try to find out which parts are taken more often and which parts are not taken more often. Like to give a very simple case, like for example, you want to profile the GCC compiler. So you can take a lot of C code and you can just pass it to the GCC compiler and try to find out which parts are more heavily executed, which parts are less heavily executed. One very common case is, for example, error cases, right? Error cases are generally very infrequently executed. They are not executed very often. It is very unlikely that you will get an error. Like for example, your AC's thermostat, right? It also has it says that, okay, if there is overheating, then switch off, right? But how many times is that code executed? It is very unlikely that it is executed a lot of times. You see that, right? So there is always, any program has these frequent paths and infrequent paths, and you can do this profiling to find out which paths are frequent.
So, just a follow. So, this SSA conversion is in static, completely static, and you are adding some dynamic information here. So, you are making a combo of both. Right? Is it? Right?
That is a very good way of looking at it. Yes, that is a very good way of looking at it. So once you have, so this is capturing some sort of dynamic information. And now what I can do is I can do static analysis with this dynamic information. You see what I'm trying to say?
Yeah.
Right. So now it is not a dynamic analysis, but it's still a static analysis. But I have added some dynamic information to that static analysis. Now I'm doing static analysis with some dynamic information. So that is what it allows you to do. That is really cool. I'm really very happy about this piece of work, and we are planning to push this in LLVM very soon. So we are actually working on it. I mean, we had prototype implementations for publishing our papers, but they were not very robust. So now actually we are building, and we are in touch with some companies, and we are trying to, they are interested in using this. And so we are trying to push it in the LLVM main branch. And I'm hoping if everything goes right, in another maybe a few months, you should have it in the LLVM main branch, this form. You should be able to use it, and you do your analysis with this. And you can really check out this paper. In fact, I mean, this paper starts off with showing that, in fact, the later part of the paper is about an optimization that we did on using HPSSA, which this hot path SSA. And it's a very trivial. So the cool part about this work is that, so you have this safe world, which is this, you do not add in your dynamic information, and you sort of have this unsafe world, or which is using some sort of dynamic analysis, but allowing you to do more aggressive optimizations. Now, people, what they used to do is they used to take some algorithm here, and they have to, like, from scratch, completely scratch, compute a new algorithm here, create a new algorithm here. And it used to be a paper. I mean, you used to take a work here, and you say, how can I do it if this dynamic information is available? And they used to write one paper completely on saying that how can I do this analysis that you people already knew about in the static world, and adding dynamic information, how they can do that work. Now what it allows you to do is that I can simply borrow a algorithm here directly, push it through HPSSA, and almost the same analysis can be used here. So the algorithms become transferable in some sense. So of course there is a small tweaking you have to do. You have to do some small business. You have to handle this tau node separately. So those things have to be done slightly. So in fact, the paper, especially this paper, talks about that. I mean, it says that how we took one very common analysis in the safe domain, and with a very small tweaking, we were able to make it into a speculative analysis, which could make use of this dynamic information. And I'm not lying. I wrote that thing in half a day. Like in an afternoon, I sat back and wrote this whole analysis myself and implemented it within a compiler. So it is that easy to do. So I already had an implementation of the original algorithm in the compiler, which was working on the safe information without any dynamic information. And I already had the implementation of HPSSA, which I'd already built. And it took me one afternoon to write a new analysis, which can also take care of this, make use of this dynamic analysis. So that is why it is pretty cool that it can do that. So that's what I'm putting a shameless plug, but I just look out for it, just check it out. I'm hoping that very soon we will be able to, like, we have a couple of interns currently working on building it into LLVM. If everything goes right, we should be able to push it into the main branch.